In this video, we're going to take a look at angular and tangential motion. Remember that tangential motion really just means like your linear, or sometimes it's called translational motion. So x, v, and a, the displacement or position, velocity, and acceleration. And it goes like this. Let's start by remembering what angular position is. If you have a circle with some radius r, and then I'm going to draw this terrible circle. So if you have some weird looking circle with a radius r, and you travel that exact length, the radius, around the circumference, which we'll call that an arc length of s, then we can say that your angular position is 1 radian. Because basically, when we want to try and define your position of an angle in terms of the radius, you take however far you've gone along the circumference, and then you divide it up into radiuses. So mathematically, we just say your angle theta is equal to s, the circumference that you traveled, or your arc length that you traveled, and then divide it up into radiuses, r. Okay, so this means effectively that if you want to find your linear distance, which is really what, oh, there should be an N there. Wow, really what the arc length is. If you want to find your linear distance, then you just need to take your angular position and multiply it by r. So that is how you can find how far forward an object has gone. Hopefully you did that in like a pre-calc or some sort of math, I don't know, 17 or 8, 2, 3, whatever class that you did. Pretty simple. We'll do an example of it together. Where things are maybe a bit new is linear velocity and linear acceleration. You can find these things the exact same way. To find the linear velocity, you take your angular velocity, which we use omega to say, and multiply that by the radius. To find your linear acceleration, you would take alpha, your angular acceleration, and multiply it by the radius. This becomes an incredibly important key, or like legend, that you can use to translate angular and linear motions into one another. Let's do 2 examples. Your bike tire has a radius of 28 centimeters. Starting from rest, you speed up for 8 seconds. At this moment, your bike tire is rotating 2 times per second. How far did you travel? Okay, so first I'm going to set this problem up by thinking about the bike tire and how, if you can hear my son in the background, he's having a great time. And the bike tire is going to travel a linear distance forward, and basically that linear distance you can think of as the arc length, or x, because when you take that arc length and kind of lay it out along the path, you'll get that straight line distance that you've traveled. So we want to find s, the arc length, because that's effectively our linear distance traveled. To do that, we are going to need to know the angular position and the radius. So the radius isn't 28 centimeters, it's half of that, which would be 15 plus 4 is 19 centimeters, or 0.19 meters. And we know that you start from rest, so your initial angular velocity, you call that omega I, is 0 radians per second. And your final is 2 times per second. So I'm going to write it like this: 2 revolutions per 1 second, because it means you're rotating 2 times. We have to, of course, get that to radians per second. So to do that, I'm going to put 1 revolution on bottom, 2 pi radians on top. Maybe you can do this in your head. And this tells me that I'm going to have 4 pi radians per second as my final angular velocity. Okay, so we want to figure out s, how far that you've traveled, and I know that the time it takes is 8 seconds. Now that I have all this information laid out, remember what I want to find is s, the linear distance traveled, but first I have to figure out the the change of angle theta. how far you've rotated in order to get that. I don't have too much information here, but if you remember sort of a secret equation, you always know that the change in the angular velocity, which in this case we can really just think of this as delta theta if you want, is the average angular velocity with time. And the average angular velocity would be those two velocities added together and then divided by 2. This is sort of like a secret or less used motion equation. Okay, so I would take 4 pi radians per second. The initial is 0, so I would add nothing to that, and then multiply that all by 8 seconds, which is going to give me half of 4 pi is 2 pi, and then times 8 is 16 pi, so 16 pi radians. And you can leave it in 16 pi radians if you want. You can also get a number. 16 pi radians will give us a number at some point. But we are going to use it to find the arc length, S, which is going to be our change of theta, delta theta, times r, which, again, delta theta and theta are somewhat interchangeable because you're just saying that theta is the change of your angle. So 16 pi radians times the radius of 0.19 meters, and that is going to give you 9.55, we'll say 9.6 meters. So that's how far you've traveled in that 8 seconds. Let's do one more problem. You get bored and decide to waste a roll of toilet paper that is 10 centimeters in diameter. So you hang a small action figure on the loose sheet and let it unroll. After releasing the toy from rest, it takes 0.9 seconds for the sacred paper to unroll 3 times. What is the linear acceleration? Okay, so if I was going to draw this, I'd have a roll of toilet paper and a little tiny action figure hanging off to the side. You're getting so bored. Immediately, I would need to recognize that the radius is 5 centimeters, which would be 0.05 meters. And it tells me that the time it takes to fall is 0.9 seconds, and the paper unrolls 3 times. So that is going to be our change of angle, or our angular position. 3 times. Well, so 3 rotations, or revolutions, to get that into radians, you would think in 1 revolution there are 2 pi radians. So there are 6 pi radians in that 3 rolls. I'm going to erase this and just write that 6 pi radians. Great 6. Okay, so that's my change of angle. Now, ultimately, I want to find the linear acceleration. But remember, the linear acceleration can be found with the angular acceleration and the radius. I know what the radius is, so what I'm going to do is I'm going to look to see if I can find the angular acceleration in an angular motion equation, and then use that to get my linear acceleration by multiplying it by 0.05. I'm given time, I'm given the angular position theta, and I'm also given the fact that it starts from rest, which would tell me the initial angular velocity is 0. All right, then to find the angular acceleration, I would use the equation with theta, alpha, and omega naught. Again, remember that we can say delta theta is effectively theta as long as our initial angular position is 0. Okay, the initial angular velocity is 0, so that whole term disappears. And now to find angular acceleration, fishy, I would multiply both sides by 2. Sorry, get rid of that plus sign. And then divide both sides by t squared. Now I can find the angular acceleration is 2 times 6 pi radians divided by 0.9 seconds. This is going to give me, oh wait, I almost made a huge mistake, 0.9 seconds squared. This is going to give me 46.5 radians per second squared. Now to find the linear acceleration, I simply take that angular acceleration and multiply it by the radius. So 46.5 radians per second squared times 0.05 meters, which gives me 2.325 meters per second squared. Now you have found the linear acceleration. Congratulations. This video is done.